Okay, the next type of rational functions that we want to consider are rational functions with oblique asymptotes. Rational functions with oblique asymptotes. So let's start with the definition. Let's see which function is said to have an oblique asymptote. Let f of x be a function. We say that y equals, let's say, mx plus b. Or let me say ax plus b here. Ax plus b with a not equal to 0 is an oblique asymptote for f of x if limit f of x minus ax plus b as x goes to infinity becomes 0, or limit f of x minus ax plus b as x goes to minus infinity becomes 0. So let's look at this definition. First of all, the definition, I'm talking about the line y equals ax plus b with a not equal to 0. Why am I assuming that a is not equal to 0? Because I want to define an oblique asymptote. If a is 0, then you will have y equals b a constant function, which is horizontal line, not oblique. Right? So that's why we assume that a is not 0, because we want to define an oblique asymptote here. And we're also talking about the limit f of x minus ax plus b to be 0. Why do we require this limit to be 0? Well, basically, asymptote means the function, if a line, for example, is an asymptote for a function, that means the function will get closer and closer to that line as x goes to infinity. So if this was the concept we used for horizontal and vertical asymptote, and the same concept here. So if f of x gets closer and closer to ax plus b as x goes to infinity, means that the difference between them get closer and closer to 0. Meaning that this limit of the difference has to be 0. So let's say, for example, this could be your line y equals ax plus b. And let's say, for example, this function here, see, gets closer and closer to this line as x goes to infinity. So this is an oblique asymptote for this function y equals f of x. Now the question is, which functions have oblique asymptotes? And how to find them? So let's find a formula for a and b, and based on that we can guess, what the function must be. So what was the expression that we had here? Limit f of x minus ax plus b must be 0. So we must have, so if f of x has an oblique asymptote, y equals ax plus b, then we can say that the limit f of x minus ax plus b will be 0 as x goes to infinity or minus infinity. So what can I conclude from this? I can say that therefore limit f of x minus ax plus b divided by x as x goes to infinity will be also 0. Because if you look at this limit, numerator goes to 0, denominator goes to infinity, and 0 over infinity will be 0. So that means limit f of x over x minus a plus b over x as x goes to infinity will be 0. And limit b over x as x goes to infinity, of course, is 0. So we can say limit f of x over x as x goes to infinity minus a is 0. So that means a is equal to limit f of x over x as x goes to infinity. So once you find a, then you can easily find b as well. How can I find b? Because limit f of x minus ax minus b has to be 0. So to find b, limit f of x minus ax minus b is 0 as x goes to infinity. So that means limit f of x minus ax as x goes to infinity minus b equals 0. And that gives b equals limit f of x minus ax as x goes to infinity. Okay, so these are the expressions for a and b. So if hence, if limit f of x over x as x goes to infinity, or limit f of x over x as x goes to minus infinity exists, and exists and is finite, exists and is non-zero. So when we say exists means it must be finite as well. Right? And then we can say that then f of x has an oblique asymptote one or two has oblique asymptote or oblique asymptotes, and the coefficients a and b in y equals ax plus b can be found via a equals limit f of x over x, x goes to infinity, b equals limit f of x minus ax, x goes to infinity, or same thing for limit when x goes to minus infinity can be written. So or a equals limit f of x over x as x goes to minus infinity, and b equals limit f of x minus ax, x goes to minus infinity. Okay, so for oblique asymptote, for a function to have oblique asymptote, limit f of x over x must exist and be non-zero as x goes to infinity or as x goes to minus infinity. And in that case, if this limit here exists, meaning that it must be finite and is non-zero, then we can find a with this limit, and then b can be found with this limit, and then the oblique asymptote will be y cos ax plus b. So for rational functions, accordingly, for rational functions, for a rational function, is a f of x equals p of x over q of x. F of x will have an oblique asymptote if what happens, we want limit f of x over x, we want that limit to exist and be non-zero. If limit p of x over x times q of x, right? F of x over x in this case will be p of x over x times q of x. X goes to plus or minus infinity, exists and is non-zero. This occurs. When can I say that limit of a polynomial over another polynomial exists and it is non-zero? If degree of top and bottom are equal. Because if degree of top is more, then the limit will be infinity or minus infinity. If degree of bottom is more, then the limit will be zero. So the only case in order for have a limit of a polynomial over another polynomial to be a non-zero constant is if the degree of top is equal to degree of bottom. If degree of top is more, limit will be infinity or minus infinity. If degree of bottom is more, limit will be zero. This occurs only if degree of p of x is equal to degree of x times q of x. And this occurs if degree of p of x is equal to degree of x times q of x will be 1 plus degree of q of x. If degree of p is 1 plus degree of q, then the function will have oblique asymptote. Otherwise, it will not have oblique asymptote. So the only type of rational functions with degree of, and the only type of rational functions which have oblique asymptotes are the rational functions where degree of top is 1 unit more than degree of bottom. So let's look at an example of such function. Let f of x equals x squared over x plus 1. Sketch the graph of f of x. Okay, so let's first find the domain. The first step of it, finding domain. Solution or domain, we need to make sure that the denominator is not 0. So x plus 1 not equal to 0. That gives x not equal to minus 1. So domain or df is equal to all real numbers except minus 1, which can be written as minus infinity to minus 1 union minus 1 to infinity. And for x and y intercepts, if I replace x with 0, y will be 0, right? Which is both x and y intercept then to origin. So the function passes through origin, which means both x and y intercept. And what else? Symmetry. We don't have, because if I change x to minus x, first of all, y will be changed because the numerator will not change, but denominator changes. So the whole function changes. And also we will not have y changing to minus y, right? If I change x to minus x, y will not change to minus y. So we don't have symmetry respect to origin or symmetry respect to y-axis. So no symmetry respect to origin or y-axis. And then for f prime, then we need to find f prime of x. F prime of x, of course, I can use the quotient rule. I have a fraction here, so for finding derivative, I can use quotient rule. X squared derivative times x plus 1 minus x squared times x plus 1 derivative divided by x plus 1 the whole squared. So this is 2x times x plus 1 minus x squared divided by x plus 1 the whole squared. So 2x squared minus x squared is x squared plus 2x divided by x plus 1 the whole squared. This is f prime of x. Now if I set f prime of x equals 0, that gives x squared plus 2x equals 0. So x times x plus 2 equals 0. That gives x equals 0, x equals minus 2. So these are my critical points. Then sign chart for f prime. Let's look at the sign chart for f prime. So these are the x values. We have minus 2, and also a 0 of denominator. We said that we should include it in the sign chart. So 0 of denominator is minus 1. So minus 2 is the smallest number. We have to list them in the order. Then minus 1, and then 0. F prime here, F here. F and F prime both are undefined at minus 1 because remember, minus 1 is 0 of denominator. Okay, seems that the screen is freezed. So undefined here and undefined here. All right. Now, let's say, for example, less than minus 2. Less than minus 2, I could use, for example, minus 3 as a test point. Test point x equals minus 3. Then f prime of minus 3 will be minus 3 squared plus 2 times minus 3 divided by minus 3 plus 1 the whole squared. Is 9 minus 6 positive divided by positive, it will be positive. So positive here, negative here. At -1, I will not have any sign change because -1 is a repeated 0. There's a power 2 here. So -1 will not affect the sign. So my minus remains minus here. But at 0, again, I will have 0 is a single root, right? X times x plus 2. So 0 is a single root. So at 0, minus changes to plus. So f prime positive, then negative, then positive. So f itself increasing, decreasing, decreasing, increasing. Then I need to find the asymptotes. So asymptotes for vertical asymptotes, I can set denominator to be 0. Denominator is x plus 1. X plus 1 equals 0. That gives x equals -1. So then I can look at the left limit and right limit at -1. Left limit at -1 will be limit x squared over x plus 1. X goes to -1 minus. So that's -1 squared divided by -1 minus plus 1. This is 1 over 0 minus, which is minus infinity. And similarly, you can check that the right limit will be infinity at -1, plus will be plus infinity. So minus infinity here, minus infinity here, and infinity here. Okay, and this is for vertical asymptotes. For horizontal asymptotes, we need to check the limit f of x as x goes to plus or minus infinity. This will be limit x squared over x plus 1 as x goes to plus or minus infinity. We can use L'Hopital rule here. So limit 2x over 1, x goes to plus minus infinity, which is plus or minus infinity. So that means no horizontal asymptote, right? Because we didn't get any constant as the result, so no horizontal asymptote. Now, what about oblique asymptote? See, I have a rational function here, and degree of top is 1 more than degree of bottom. Degree of top is 2, degree of bottom is 1, degree of top is 1 unit more than bottom. So I will have an oblique asymptote. And what is the oblique asymptote here? So first I can mention here that we have an oblique asymptote. Since degree of x squared is 1 plus degree of x minus 1. And to find y equals ax plus b, do you remember the recipe I provided to find the oblique asymptote? Oblique asymptote, if you write it as ax plus b, a can be found as limit f of x over x. X goes to plus or minus infinity. So that's going to be limit of which function? X squared over x minus 1, then divided by x. X goes to plus or minus infinity. So that's limit x squared over x squared minus x. X goes to plus or minus infinity. And you can use L'Hopital, or it's easier if you just factorize x squared, highest power of x from top and bottom. So it's going to be x squared in the top and bottom x squared. Factor it out. What will be left? 1 minus 1 over x. X goes to plus or minus infinity. This cancels with this. And then the answer will be 1 over 1 minus 1 over plus minus infinity. 1 over 1 minus 0. The answer will be 1. So a, the value of a is 1 here. Okay. Now, how can I find b? A is 1. How can I find B? To find B, B is equal to limit f of x minus ax. X goes to plus minus infinity. Okay, so please remember, A is limit f of x over x. B is limit f of x minus ax. And then this is limit x squared over x minus 1 minus x. A is 1, so ax will be x. X goes to plus minus infinity. And then this is limit x squared minus x squared plus x divided by x minus 1. X goes to plus minus infinity. So then this is limit x over x minus 1. X goes to plus minus infinity. And you can use L'Hopital, or you can just factor the highest power of x out. So if I use L'Hopital here, let's say derivative of x is 1, derivative of x minus 1 is 1. So the answer is also 1. So B is also 1. So oblique asymptote here will be y equals x plus 1. Y equals x plus 1 is our oblique asymptote. So we found all the asymptotes. Now we are ready to sketch the graph. Okay, so let's sketch the graph here. Okay, so here you are, that's the graph. This is y equals x plus 1, our oblique asymptote. And the function, if you look at the sign chart, before -2, we have it is increasing. And after -2 is decreasing. So at -2, we have a local maximum. Right, so here, look at here. Increasing before -2 and decreasing after -2. Local maximum here. And how much is the y value? We can also find the y value, of course, by just putting into the function. You know, each local maximum and minimum. In the sign chart, we find the x value of the local max and min. But when you want to sketch the graph, you also need the y value. So you can easily find the y value by just simply plugging into the formula for the function. How much is the y value here at -2? We just need to find f of -2, which is going to be how much? 4 divided by -1. It's -4. Okay, so here you have local maximum here. Local maximum. And after -2, the function decreases all the way to -infinity right before -1. Look at the sign chart. Decreases all the way to -infinity right before -1. Right after -1, the function starts from infinity, again decreases all the way to 0. Right after -1, starts from infinity, decreases all the way to 0. At 0, we saw that at 0, the y value is 0, so the function passes through origin. And 0 here is local minimum as well, because see, the function is decreasing to all the way to 0 and increasing after 0. Decreasing before 0, increasing after 0 means we at 0 we have local minimum. So local minimum at 0. So this 0 happens to be x-intercept and y-intercept and local minimum. It just happens to be all the same point here. It's just accidental. So here we have local minimum. and then increasing after 0, increasing all the way to infinity. But at infinity, remember, we have an oblique asymptote at infinity and minus infinity. What is the oblique asymptote? Y equals x plus 1. What does that mean? That means the function, the graph of the function will get closer and closer to this line as x goes to infinity or as x goes to minus infinity. Okay, so x goes to minus infinity and infinity, the function is closer and closer to this line. One local maximum here because the function increasing before and decreasing after. Remember, for local maximum, the x value is given in the sign chart, but for y value of that point, you can simply plug it into the formula for the function. And we had one vertical asymptote. Right before it, the function was minus infinity. Right after it, the function was infinity. And decreasing again all the way to local minimum. Here is local minimum because decreasing before, increasing after. And the y value again can be found by the plugging into the function. And this local minimum happens to be x and y intercept as well. And again, the function goes to infinity and gets closer and closer to the oblique asymptote. Okay, so this is an example of a rational function with oblique asymptote. So we learned that which rational functions have oblique asymptotes. The rational functions where degree of top is exactly 1 unit more than degree of bottom. All right, so the next type of functions we want to look at their graphs is roots functions. Let me start with an example to see how we can sketch the graph of this root function here. Let's say x minus, let's say example, sketch the graph of y equals f of x equals x minus 4 to power 2/3, which is same as cube root of x minus 4 the whole squared. So we want to sketch the graph of this function. Let's see how we can do that. So first the domain. The domain when we have cube root, because here we have a cube root. So there is no restriction for x value. If this was a square root, then I need to make sure that the under the square root is non-negative. But for cube root, there is no restriction and domain will be all real numbers. No restriction for cube root. So that means domain is minus infinity to infinity or all real numbers. Okay, then we need x and y intercepts. So if I replace x with 0, then y will be cube root 16. So this is y intercepts. And if I set y equals 0, then I'll get x equals 4. So that's x intercept. Then for symmetry, well, there is no, again, symmetry respect to origin or y-axis. Why? Because if I replace x with minus x here, so y value will change, first of all, because minus x minus 4 squared is not same as x minus 4 squared. The minus x plus, if it was minus x plus 4 the whole squared, this is same as x minus 4 the whole squared. So this is true, but minus x minus 4 the whole squared is not same as x minus 4 the whole squared. So y will change, and y will not change to minus y either, right? If I change x to minus x, y will not change to minus y. So no symmetry respect to y-axis. Or origin. And then we need to find f prime of x. For f prime of x, I can use the chain rule. U to power m derivative is m u prime u to power m minus 1. So that's going to be 2/3. Derivative of x minus 4 is 1. And then x minus 4 to power 2/3 minus 1. 2/3 minus 1 is minus 1/3. So 2/3 cube root x minus 4. But this is of course valid if x not equal to 4, right? Because if x equals 4, denominator will be 0, I cannot use this formula. So what happens at x equals 4? How much will be f prime of 4? So you can check that f prime of 4 does not exist. Since limit f of x minus f of 4 over x minus 4 as x approaches to 4 does not exist. So you can easily check that this limit does not exist. If this limit does not exist, means f of x is not differentiable at x equals 4. In other words, f prime of 4 does not exist. Okay, so what will be the critical point here? So critical points. If I solve for f prime of x equals 0, this of course has no solution, because when you look at the formula for f prime of x, numerator is always non-zero. So if numerator is not 0, the whole fraction will not be 0 either. But there's only one point where f prime does not exist, and that was 4. F prime of x does not exist at x equals 4. So we have one critical point. Namely, x equals 4. Okay, so x equals 4 is our only critical point. And please note that x equals 4 is in domain of f. If x equals 4 was not in domain of f, we would not count it as critical point. The critical point must be always in the domain of the function. Now x equals 4 is not in domain of f prime because f prime of 4 is undefined, but it is in the domain of f. Remember, domain of f was all real numbers. So of course 4 is there as well. And therefore it is considered as a critical point because it's a part of domain of f. But f prime does not exist at 4. So one critical point at 4. Now we can use the sign chart for f prime. So here we said that in the first row, we have to list all the x values, all the critical points. We have only one here, which is 4, and then f prime here, and then f here. And so at 4, f prime does not exist. But what about f? F of 4 exists. F of 4 is how much? F of 4 was 0. This is f of x, so f of 4 is 0. Now, before 4, f prime is negative or positive. Before 4, let me use a test point. For example, 0. Let's use 0 as our test point. then f prime of 0 will be 4 over, let's say 2 over 3 times cube root minus 4, which is negative. So negative here and positive here. 4 is a root of denominator, but as we said, even a root of denominator can change the sign, because if the denominator changes the sign, the whole fraction changes the sign. So at 4, we go from minus to plus. See, this is not a repeated root, so the denominator changes sign at 4. So the whole fraction also changes sign at 4. So from minus to plus, the function f will be decreasing here and increasing here. Okay, but now one difference with the previous problems is that 4 is a 0 of denominator for f prime, which means limit of f prime at 4 is infinity or minus infinity, although limit of f at 4 is not infinity or minus infinity. See, 4 is f itself at 4 is 0, limit of it is also 0, but limit f prime at 4 is infinity or minus infinity. So here I can say note at x equals 4, f of x is continuous, but limit f prime of x at 4 is limit 2 over 3 times cube root x minus 4, x goes to 4 minus. So this is 2 over 3 times 0 minus, which is minus infinity. And the right limit of f prime at 4 is 2 over 3 cube root x minus 4. And that's 2 over 3 times 0 plus, which is plus infinity. Okay, so f is continuous, but f prime goes to infinity or minus infinity. Such a point where f is continuous at that point, but f prime goes to plus minus infinity, is called cusp. And it looks like something like this, or it looks like something like this. So see this one, when you look at this one, see limit f prime, the left limit, look at the left limit of f prime here. This function, look. This is, let's say, a limit f prime of x. The left limit here is minus infinity. Right limit of f prime is infinity. See, this function f itself is continuous, so limit f is not infinity. But regarding f prime, you have a vertical tangent line here. If x is a little bit less than a, then you have almost vertical line, vertical tangent line, but little bit, the angle is a little bit more than 90 degrees. So the slope is negative, like negative and a large number, like minus 1,000 or minus 10,000, the slope here. If x is a little bit less than a, the line is almost vertical, which means the slope is almost infinity, but in the negative side, because the angle is a little bit more than 90. So this slope could be minus 100 or minus 1,000, something like that. So that's why we are saying that left limit of f prime is minus infinity. If x is a little bit more than a, then almost again vertical line, but the angle a little bit less than 90. So the slope will be a very large number with positive sign, like plus 100 or plus 1,000. So limit f prime is infinity. But in this picture, it's the opposite. In this picture, when you look at the, again, let's say if x equals a here, a little bit before and a little bit after. A little bit before, the angle is a little bit less than 90. A little bit after, the angle is a little bit more than 90. So what can we say about f prime? So limit f prime as x goes to a from left here is plus infinity. Limit f prime as x goes to a from right is minus infinity, right? So vertical tangent lines, a little bit here, vertical, almost vertical with negative sign, so minus infinity. Here, almost vertical line with plus sign, so plus infinity. This one also plus infinity, this one minus infinity. So we can have each of these two points is called a cusp. The point is called the cusp here. So both of these are called cusp. But this one, you know, the left limit of derivative is minus infinity, right limit infinity. This one, left limit of derivative is infinity, right limit is minus infinity. Okay, so which one is the case here? Here we had f prime. Before minus 4, we said it's minus infinity. And after 4 is plus infinity. So we have a picture similar to the first left picture here. Before it's minus infinity, derivative is minus infinity. And after the point, the derivative is infinity. So let's sketch the graph now. Sketching the graph. Sketching the graph. So we don't have any asymptotes here. So again, I want you to notice that limit f is not infinity or minus infinity. If limit f was infinity or minus infinity, we would have a vertical asymptote at that point. But that's not the case. Look at the formula for f. This is the formula for f. Obviously, f has no vertical asymptote. See, there is no denominator or anything. And the function is continuous everywhere, and the domain is all real numbers. So there is no asymptote. So because limit f is not infinity, limit f prime is infinity. Limit f prime being infinity doesn't mean asymptote. It means a cusp. Cusp means something like that, means a vertical tangent line. Okay, so this is maybe the most important, one of the most important, or maybe the trickiest, if not the most important, at least the trickiest point of today's lecture, that limit f being infinity or minus infinity means vertical asymptote. Limit f prime being infinity or minus infinity doesn't mean vertical asymptote. It means a cusp, means a vertical tangent line. Limit f being infinity means vertical asymptote. Limit f prime being infinity means vertical tangent line. So please remember this. Okay, so at x equals 4 here, we have a cusp. So let's say this is 2. So this is 2 and 4 here, let's say. And the y value is also 0 at 4. Remember, 4 was x-intercept. And the function is decreasing before and increasing after 4. And how much was the y-intercept? Y-intercept was cube root 16. You see the function will be decreasing and then increasing. And this point is cube root 16, the y-intercept. And this is the local minimum, right? See, at x equals 4, decreasing before, increasing after local minimum. But please remember that to sketch the graph, in addition to the x value of local minimum or maximum, we also need the y value. How can we find the y value? Just plug the x value into the original function f. F here, original function f is this. If I replace x with 4, I'll get 0. So for local minimum, which is this point here, x value is 4, y value is f of 4, which is 0. So that means the point is on the x-axis. The local minimum, since f is decreasing before and increasing after 4. But in addition, this number 4, in addition to being local minimum, it's also a cusp. Because limit f prime of x as x goes to 4 minus was minus infinity, and limit f prime of x as x goes to 4 plus is plus infinity. So this 4 is local mean, also is cusp. Local mean because decreasing before, increasing after. Cusp because it's a vertical, it has a vertical tangent line. Before for vertical, almost vertical with a negative sign, after for almost vertical with positive sign. Okay, so this is the graph of this root function. So for root functions, you have to be careful and aware of cusps. The points with not with asymptotes, but with vertical tangent lines. Okay, guys, so today we covered rational functions and root functions and how to sketch them. So we still need to do some examples for trigonometric functions and exponential and logarithmic functions, and to see how to sketch those types of functions. And I'll explain about those types of functions next time. Okay, guys, so thank you and see you next time.